Thank you very much, Heike. My warmest welcome, colleagues. Greetings from California. And it's my fervent wish that you and those closest to you remain in good health at this time. So let's go to the classroom for a moment. Let's go to a graduate course on catalysis. It's taught by a member of 2 national academies. And in the context of that course, our colleague asked the question, should you do NMR? And his response is, you should never do NMR. Why? Because it is the least sensitive spectroscopy you can imagine. It's a technique in which the qualitative and quantitative results depend on how you execute the experiment. It's a methodology guarded by a protective and exclusive community. It's capital equipment intensive. The image in the background should remind you of that. And as some funding agencies have noticed, NMR produces fewer papers per capital dollar than most other methods. It's fraught with high operating costs, and therefore don't bother doing NMR when you do catalytic research. Well, why would you even bother in the first place? So I'm going to show you as an example just one spectrum. It's a Deuterium Nmr spectrum, and here's what it looks like. It's characterized by a very broad line, which you might think uninformative. But let me just remind you, first of all, that NMR has the advantage of being quantitative. The area under the signal compared to a standard gives you the number of moles or micromoles present in your sample. And such quantitation, as you know from liquid organic synthesis NMR spectroscopy, such quantitation can be extremely valuable. Even though the line is very broad, its center of mass can be determined quite accurately. And from this particular experiment, I discern a chemical shift that's consistent with an amide bond. The shape of the line is unusual, isn't it? It's consistent with electric field gradients that are present in an ND3 group. And so not only do we get the local bonding, but we get the distribution of that local bonding in the immediate environment. And of course, that splitting tells us that the deuterium is consistent with a triad spinning about its C3 axis. So the reason you do NMR, even though it has many disadvantages, is that it can provide how much is there, who it's bonded to, how the bonds are distributed in space, and the dynamics of how they're moving. And that's the reason why we bother. And the trick and the key for the MOF chemist is to imagine what problems can be uniquely solved with these strategies and then deploy them in MOF research. So in the next 20 minutes or less, if I can time myself properly, I would like to look at NMR as applied to various challenges in MOF research: synthesis, crystallization, defects, properties, de novo creation for function, local bonding structures and distributions, and dynamics. I will, in the course of this talk, refer to papers in the literature. These are what I call the Reimer group favorite papers. They are not comprehensive list, and my sincere apologies if your paper is not here. It's simply because in the time allotted, I just couldn't include all the works. By the way, if you're interested, notice on the bottom there's a link on the internet, and you can go to that link right now, download a PDF of this lecture, and either follow along so that you have all the references. And then, of course, I will include an example from my group in slightly more detail because you can hold me accountable for the work that I've done. All these things are post-MOF 2018, that is after Auckland, so that we're looking at the most contemporary research. A key attribute of NMR that is persistent in almost all these studies is the concept of magic angle spinning. The magic angle is 54.7 degrees. And so your sample, which you are accustomed to thinking of as in a glass tube inserted vertically in the magnet, here it's in a cylinder and it's packed inside of a so-called rotor, and that rotor is kinked at the 54 degrees relative to the magnetic field. Why is that a magic angle? It's magic because that number placed into this equation yields 0. It turns out that many of the interactions that give rise to broadening in solid state NMR go as this second order Legendre polynomial, where theta is some angle on the molecule relative to the magnetic field. By rapidly spinning, all angles are averaged to this average number, producing 0. And so that's all I'm going to say about NMR methods in the course of this talk. But I just want you to remember that when you go to do solid state NMR for your MOF research, you will almost certainly be doing magic angle spinning. So what about synthesis? Recent papers have included such topics as nucleation, pore formation, defect engineering, post-synthetic modifications, and rapid screening. And of course, these references are down here. And again, if you want to, you can pull a PDF of this lecture. Let me just mention that Kenneth Harris at the University of Cardiff has a paper on archive referenced here, soon to be published. A lovely piece of work. Now imagine inside of this cylinder, you have a liquid solution in which MOFs are growing. So you can relatively easily, as Professor Harris shows, you can acquire a liquid state NMR of the synthesis broth and a solid state NMR spectrum of the growing crystallites at the same time. And in so doing, Professor Harris and his colleagues looking at this particular MOF formation, for example, can get the probability of nucleation, can get Arrhenius data for the nucleation and for the growth of crystallites in these materials. Very exciting example from the literature on the use of NMR for synthesis. In my group, we became interested working with Omar Yagi in chemical reactions in which we would transform a COF from one chemical structure to another. These are solid state reactions. So notice here, we're going to start with a crystalline COF. We're going to conduct 1, 2, 3 separate reactions to produce cyclic carbamate COFs. These reactions take place in the solid state. One of the products is not even crystalline, although it retains this well-defined conductivity. The question is, can I follow with solid state NMR the course of this reaction, just like you might do with liquid state NMR in an NMR tube? And the answer in this case is that we are going to use nitrogen-15 NMR, and we're going to follow this nitrogen through the course of these reactions. So the synthesis for compound number 1, here's compound number 2, compound number 3, here's 4, and separately for the sulfur group. So here we have the ability to quantitatively discern nitrogen-15 shifts and thus get yield. So these are the yields of these products during the course of this reaction, all obtained with quantitative N15 MAS NMR. What about structure and local bonding configurations? Here, there are several recent papers in the literature that look at, for example, short range order in MOFs and MOF classes, intermediate and medium range order with a technique called spin diffusion, which I'll say a moment about in a minute. And of course, the interface between MOFs and polymers that surround them, for example, in membrane research. And here are a number of interesting papers that you can go to in the literature to follow up on those. Let's just take MOF glasses for a moment as an example from this particular reference, number 7 on this list. And the idea, the question here was, if I make a multivariant MOF, and in the crystalline form and in the glassy form, is the distribution of linkers in both those forms similar? Well, the answer can be discerned by doing rate measurements. It's a funny rate in NMR. Here's a peak, carbon-13 peak associated with one linker. Here's a carbon-13 peak associated with a different linker. And the rate measurement asks, how do those peaks grow with time? And this time is an experimental parameter. And the rate at which they grow is proportional to the spacing between the linkers in the crystalline material. And similarly, you could do exactly the same experiment in a glassy material because NMR does not require a regular crystal structure to get these local short-range orders. And these experiments were conducted and the authors were able to conclude that in both the crystalline and glassy forms of this MOF, the distribution of linkers was random. In my particular case, we are interested in discerning the structure and local environment of a catalytic site. And in particular, we want to know where is the action happening from a chemistry point of view. So we're going to start with MOF 808. It's a zirconium-based MOF whose structure is shown here in this particular slide. And it has a reasonably good surface area, a couple of square kilometers. And as you probably know, this MOF is very, very stable. It can be sulfonated with dilute sulfuric acid, produce what is known as a sulfonated MOF 808. It's a heterogeneous acid catalyst, and other groups, including our own, have shown that it exhibits very good catalytic performance, for example, to dimerize isobutene with 100% selectivity to C8. So it's a very nice catalyst. The question is, where's the action? And if you do stoichiometry measurements of these systems, you would discover that there's at least 2 different structures that are possible that would be consistent with the numbers of protons, oxygen, sulfurs, and so forth. So which one is it? Well, one way to probe that is to, first of all, start with an NMR probe that assesses the acidity of a particular site. In this particular case, we're going to use phosphorus 31 NMR, and we will use the trimethylphosphine oxide molecule as a probe, where this particular hydrogen bond influences the phosphorus chemical shift in a way that's linear with respect to the acidity of the proton. Here's the proton NMR of trimethylphosphine oxide adsorbed on dehydrated sulfonated MOF 808, and here it is hydrated. And you'll notice the appearance of this peak at 69 ppm. That's the triphenylphosphine oxide bound to the acid site, and the value 69 ppm tells us that it is indeed a very good, a very strong acid catalyst. So now we can do proton NMR with these magic angle experiments to try and get a high resolution proton spectrum and ask, what can we discern about the role of water in this system, since water appears to be necessary for the catalytic activity. On the left over here, you see the proton NMR spectrum of the MOF in its dehydrated form. These are protons on the linkers, OH groups, and so forth and so on. And here it is in the hydrated form. So we have 2 peaks that have appeared in the hydrated form. We added an H2O, right? But there are 2 different chemical shifts for the proton peaks. Well, that's unusual. And so what we can do now is deploy a multiple quantum or a multi-dimensional method where on one axis we have the proton NMR spectrum. So here's 2.5 ppm here, here's 8.7 ppm here. And the fact that they are split along this line tells us that those 2 protons are close to each other. So these 2 protons are indeed the water molecule. That's further affirmed by looking at the double quantum dimension of this experiment and noticing that this peak at 11.2 ppm on this dimension matches the sum. So proton NMR then has shown it is the water molecule that's associated with the acid site, and the water molecule has 2 different chemical shifts. The deployment of DFT then tells us that indeed this particular acidic proton is responsible for the catalytic activity. Again, a structure property relationship, a relationship determined by NMR. I know many of you are interested in dynamics. For example, the dynamics of adsorbates and linkers, very profitable fields of study for many. Here are some papers, some favorites of my group. Gate opening effects that can be measured with NMR, gas diffusion measurements, multi-site exchange. And I will mention 2 of these for your curiosity. This very busy panel can be explained pretty quickly. We're going to look at methane. In this particular MOF, it's magnesium MOF 274, and ask the following question. What is the nature of the exchange between methane bound to an open metal site and methane that's in the pore? And we serendipitously discovered that the NMR relaxation times of the methane protons, 1 over that time is a rate, and that rate has a peak as a function of how much methane you put inside the system. This is, if you like, the pressure as measured by the number of methanes per metal eye. My colleagues who do dynamic simulations, molecular simulations, can put methane in this system and conduct calculations using the force fields that are known for this system. And they discern, interestingly enough, that there's a minimum in the exchange rate computationally between these 2 sites at about the same partial pressure as this maximum. So it turns out the NMR has discerned this exchange rate when the exchange rate happens to match in time scale the NMR time scale, which in this case is 1 over the NMR frequency. Interestingly enough about that, if you look at the maximum of those rates, or the minimum in the T1 if you like, as a function of different metals, you discover that these maxima are nicely proportional to the adsorption enthalpy. So not only were we able to discern the rates, but we see that the magnitude of the fluctuating magnetic fields that give rise to relaxation scales with adsorption strength. Perhaps the most popular dynamic method that you might be interested in is pulse field gradient NMR, of which I will not describe, but I'm sure you're very familiar with it. And so what we decided to do was look at MOF crystals now that are grown from solutions in which the MOF crystals are very big. And why did we want them big? Because we want to look at diffusion inside the crystal of small molecules like CO2. And we are not particularly interested in this experiment for looking at diffusion of CO2 between crystallites. So we grow big crystals and conduct self-diffusion measurements of CO2 in this particular MOF, magnesium MOF. And sure enough, as a function of pressure, you see that there's not much changing. And this is due to the fact that we're just looking at CO2 moving up and down these one-dimensional channels in this material. Surprisingly, we were able to discern that there's a diffusion coefficient of CO2 from one channel to another, a so-called perpendicular component. Various calculations and simulations show that in a perfect crystal, that should not be possible. And the magnitude of these differences is about 2 orders of magnitude different. So how could this possibly happen? And the answer, of course, is there must be holes and defects in these materials. And very rarely, one of these CO2 molecules can jump from one tube to another. And we have indeed discerned this to be true, because if we make the MOF 274 crystals with the most sensitive crystal growth methods that are extremely slow, we can completely suppress this perpendicular component. We can also change the size of the pore by changing the linker. Again, this is the MOF 74 family, and measure the self-diffusion coefficients as a function of pressure. And as you might expect, the bigger MOFs have faster diffusion by about a factor of 7 than the smaller MOFs. So let's turn to structural property relationships at minute 13 in the talk. And there the question is, if I systematically vary the structure of a MOF or its appendages, what are the variations in the properties and how do I discern them? This is really at the heart of materials chemistry for generations. So there's a host of interesting papers recently that have explored this, including, for example, in paramagnetic MOFs. We heard about EPR for NO2 absorption. Negative gas absorption is a particularly interesting phenomenon as discerned by a variety of techniques. And I'll mention that briefly because I find it so utterly fascinating. And it is a complete coincidence that it happens to be related to the Technical University of Dresden. Yeah, so now we're also going to be doing carbon-13 Mas Nmr, and we're going to examine a family of MOFs. Sorry, we being the imperial we, it's actually our colleagues in Dresden who did this work. And what they've decided to do is grow a series of MOFs in which the linkers are of varying length to make the pore sizes larger and larger. And they have ascertained that these materials respond to pressure by opening and closing. So here's the open structure as determined by the authors, and the closed structure. And the interesting intellectual question is, when these open and close, is it possible that they close in such a way as to compress the gas inside the pores and yield the so-called negative gas absorption? Here's the carbon-13 Mas Nmr spectrum of these materials in argon and in butane. And the authors were able to use the carbon-13 chemical shifts of the linkers to discern that, in fact, indeed, these open and closed structures are consistent with the NMR. But what was particularly fun about this paper, which I enjoyed so much, is that this particular MOF, which does exhibit the negative gas pressure, shows that butane can be trapped in the closed system and in such a way as to clamshell on to this butane and hold it in the system. Very lovely work from our colleagues in Dresden. As many of you know, my group is particularly fixated on carbon capture with amine-based systems. As we heard in Martin's earlier talk, carbamate chemistry is the favored method for doing this, where the acid-base reaction forms a carbamate. This is reversible so that absorption occurs here to form the carbonate. Desorption is the reverse reaction done by heating. Again, we do love the MOF 74 family of materials because, as you saw earlier, they have open channels with facile diffusion. The density of the open Lewis acid sites is very, very high. So what we can do is use, for example, diamines, and we can take a diamine, bind one end to the metal atom, have the other end dangle into the pore to snatch our CO2 as it comes by to do the carbamate chemistry. So we've been involved in this work with the long group for several years now, and we have a variety of MOFs and a variety of diamines, and NMR principally, though not exclusively, has been responsible for determining the chemical mechanism by which CO2 happens. In all these systems, what's particularly exciting is that the adsorption occurs very, very rapidly in a chain reaction that produces carbamates, typically along the walls of the tubes. And carbon-13 NMR has shown that for some diamines, you form ammonium carbamate chains. For other diamines, you actually get carbamic acid pairs on either side of the pore, and the acid groups span the pore. And for other amines, you actually get a very unusual case where carbamates line one side of the pore and carbamic acids line the other part. These structures and mechanisms were largely determined by carbon-13 NMR, N15 NMR, and a double resonance experiment, which shows how close nitrogens and carbons are to protons. Well, this is all very good and well, but alas, these materials do not exhibit the kind of long-term stability that's needed to deploy them in, for example, a coal-fired or natural gas-fired power plant. And the reason for that should be pretty obvious to all of you, that if you use steam to desorb CO2, as would be expected in industrial practice, you wind up volatilizing the amine and reacting with CO2 with the metal site. So the Long Group and their colleagues came up with this clever idea of building a tetraamine in which the amine functionalities would bind to the metal, and the other two amines would be responsible for snatching the CO2 as it came by. And the key, of course, is to get this length right. So this was done. Here, for example, is an X-ray structure of the zinc analog. And the zinc analog shows exactly what you'd expect, namely that you have a metal nitrogen bond at one end of the tetraamine and a metal nitrogen at the other end of the amine. It's the magnesium compound, though, that exhibits the kind of chemistry that we need in order for these experiments to be effective. So how do we know what's there with the magnesium MOF? Well, let's take a look at carbon-13 NMR of this particular MOF with this particular tetraamine. And even though the peaks are different heights, they are the same area, which tells us then that the product that's formed in the carbamate chemistry is symmetric. The N15 magic angle spinning NMR tells us that before CO2 adsorption, we can see the primary and secondary amine sites. And after absorption, we see the carbamate and the ammonium. And I know what you're thinking. No, nobody would publish this kind of signal and noise, but the answer is we've done hundreds of these measurements, and we know with high confidence the ammonium and carbamate shifts for these materials. So the product is ammonium carbamate. And then finally, if I look at carbon-13 NMR of C13 CO2 adsorbed on this system, I find it has a single peak, a single chemical shift. That chemical shift here, 162, can be parsed via a multi-dimensional experiment into those that are proximate to the amine nitrogens and those that are proximate to the amide groups, and amine nitrogens. So ammonium carbamate chains are formed, and I'm going to skip a few of these topics because in the interest of time, I want to finish in 1 minute, if I can, Ike, in 1 minute, with the de novo creation of a MOF. And as I mentioned, I'm sort of fixated on carbon capture for environmental mitigation. And to design a MOF from scratch, what would you think about doing? Well, we can turn to pharmacologists and ask, how do they actually design small molecules to do the kind of medical needs? And the answer is they know the structure of the protein or the biomacromolecule, and they use computers to screen small molecules that fit them. And this is, they're called pharmacores. Our problem is very simple. We need adsorbophores. Why? We know exactly what the small molecule is, carbon dioxide. We need to know the structure of the macromolecule that binds it, and it has to bind it exclusive from nitrogen and water, which make up a significant part of these flue gases. So how do you do that? Let's go to a database, use Monte Carlo methods to calculate the adsorption isotherms or the Henry coefficients for a few 100,000 hypothetical MOFs and ask which ones separate CO2 from nitrogen. Most don't. A few do. So let's take those 8,000 ones that have high selectivity and high capacity, and then calculate the active site using the computer, and then Having calculated those sites, we're going to bin them to structural types using graph theory. These structural types are the adsorbophores. And those structural types then can be assessed further for whether they have affinity for water and an affinity for CO2. And where we want to be is on this side of the axis where we have a high affinity for CO2 and a low affinity for water. And these are some of the adsorbophore types as shown here. Clearly, parallel aeromagnetic rings look like a good one. And from our library, we identified 13 of these MOFs that exhibit this kind of structural feature. And then the key is to go to the lab. Go to the lab and make them. And we were able to do them as this particular structural diagram shows. Here it is here, M8067. It's an aluminum MOF, very stable. It has a nice spacing between the planar aeromagnetic rings. And the theoretical values for the adsorption isotherm that drove the whole analysis in the first place turned out to be a pretty good match with the experiment. So our design principles were based upon pretty good Monte Carlo molecular simulations. These cycle well. The aluminum MOFs have good cycling and pretty good capacity. That's good news. So now let's turn to the NMR portion. And now we're going to look at carbon-13 NMR of these particular MOFs as a function of how much water we're going to add. And the key parameter here will be line width, because as water goes into this MOF and gets proximate to the carbons, we expect a change in that line width. And interestingly enough, up to about 60% relative humidity, none of the carbon-13 line widths are affected. And only at the very highest humidities do we begin to see the effects of water on those carbons that are proximate to oxygens. How about C13CO2 itself? In this same experiment, we can see that water appears to have no effect on the line width of C13CO2. This experiment is sub-ideal, however, because the magic angle spinning, although slow, still interferes with the broadening mechanism. So we'll just turn off the magic angle spinning and do static carbon-13 CO2 as a function of relative humidity. And as you can see, there are subtle changes in the line width, but no substantive ones with relative humidity. And in particular, if I use D2O instead of H2O, there's no change in the line width, which means the static NMR tells us then the material does absorb CO2 and it does it at the exclusion of water, even though water is present. So the adsorbophore was designed via computation. It was built via synthetic chemistry, and NMR says that it operates as designed. Well, in closing then, I just want to point out we visited synthesis, properties, function, structure, dynamics for a variety of systems with papers from both the literature and my own group. All these are relatively recent papers. I'm extremely grateful to my group. Dr. Alicia Lund here and Dr. Lena Funke helped prepare the material for this talk. The experiments from my group that I talked about, two fine postdocs, Alex Force and Rich Bounds. Rich is at the University of Cologne now. Alex is at Cambridge. Tom Popp and Valencia Witherspoon were my PhD students. They are both postdocs now. I'm grateful to the US Department of Energy. But of course, these are the NMR leaders of the work. We have fabulous co-authors from my colleagues with whom I share this work, synthetic chemists, computational chemists, and the like. And I do thank you very much for your attention. If you go to the PDF, you can find a list of the papers that I talked about from my group. So with no further ado, then Professor Brunner, I turn the floor back over to you, and I'm sorry I went over just a couple of minutes. Please forgive me.